Good morning everyone. Today we'll be presenting on CPU schedulers and their types. Let's dive into how modern operating systems decide which processes get to use the CPU and when. What is CPU scheduling? In a multi-programming system, multiple processes compete for a limited CPU time. The CPU scheduler is responsible for deciding which processes run next and for how long. Good scheduling helps maximize CPU utilization, improve response time, and ensure fairness among all running processes. Without it, our systems would feel slow and unresponsive. Process state transition. A process goes through several states: new, ready, running, blocked, and terminated. The scheduler mainly works between the ready and running states, deciding which processes should move to execution next. Scheduling criteria and performance matrix. We evaluate scheduling algorithms using metrics like CPU utilization, throughput, turnaround time, response time, and waiting time. An ideal scheduler keeps the CPU busy, completes more processes in less time, and minimizes the delay user experiences. First come first serve (FCFS) scheduling. The simplest method is first come first served. Processes are handled in order they arrive, like a queue at a ticket counter. It's easy to implement but can cause long waiting times, especially if a big job blocks shorter ones, known as convoy effect.
Shortest job first minimizes the average waiting time by picking the process with the shortest CPU burst. It can be primitive, non-primitive, but predicting the job length accurately is the main challenge. That's why system uses historical data to estimate process times. Priority scheduling. Here, every process is assigned a priority value. Higher priority processes are executed first. To avoid starvation of lower priority processes, we use a technique called aging, where priority waiting processes gradually gain higher priority. Round robin scheduling. Here, round robin gives each process a fixed time slice, like each player taking turns. Is great for time sharing systems because it ensures fairness and quick response. However, choosing the right time quantum is critical too. Small causes overhead, too large behaves like first come first serve. Advanced scheduling algorithms. More advanced algorithms include multi-level queues, multi-level feedback queues, and scheduling. They separate system, interactive, and batch processes into different queues and dynamically adjust behavior based on system load. Just like how modern OS adapt to user activities. In real-world application, modern systems use hybrid schedulers. Linux uses a completely fair scheduler. Windows even employs multi-level feedback queues, and Mac OS builds on the Mac kernel. Scheduler in real-time systems like autopilot software must meet strict time guarantees.
Real-time scheduling is used where timing is everything, like in hospitals, autopilots, or industrial control systems. There are two kinds: hard real-time, where missing a deadline means failure, and soft real-time, where delays are acceptable but undesirable. Two major algorithms handle this. There are rate monotonic, which gives fixed priorities to frequent tasks, and earliest deadline first, which always runs the most urgent tasks first. The key metric here is how often deadlines are missed because in real time every millisecond counts. Multiprocessor and multi-core scheduling. Today's CPU have many cores, so scheduling isn't about just one processor anymore. It is about teamwork. In asymmetric multiprocessing, one main core makes all scheduling decisions. It is simple but can slow things down. In symmetric multiprocessing, all cores make their own scheduling choices, which improves performance but adds complexity. Schedulers like Linux's completely fair scheduler constantly balances load across cores, make sure all processors share the work efficiently, just like keeping every checkout counter open in a busy supermarket. Energy aware and thermal scheduling. Modern CPU don't just focus on speed, they also manage power and temperature. Techniques like dynamic voltage and frequency scaling adjust CPU speed depending on workload, saving energy when possible. Ideal scheduling puts unused cores to sleep, and thermal scheduling moves hot tasks to cooler cores and prevent overheating. This is crucial for smartphone and IoT devices where battery life matters. These schedulers make sure performance stays smooth without wasting power or overheating. Machine learning based scheduling. Machine learning has entered CPU scheduling too. Instead of fixed rules, modern systems learn how programs behave. They predict how long tasks might take, adjust time slices dynamically, and classify workloads. CPU heavy, interactive, or background. This means your device can prioritize what matters most. Maybe your call app in the morning, your ID in the afternoon, and your game in the night automatically. In the next step towards computers that optimize themselves. The scheduling algorithms show down. There is no single best scheduling algorithm. Each has strengths. FCFS is simple but slow with long jobs. SJF is efficient but hard to predict. Priority scheduling is powerful but can cause starvation. Round robin is safe for users but has context switch overhead. Multi-level feedback queues balance everything but are complex. Modern systems combine them. Your operating system might use multiple at once for different tasks. Together, they keep your system fair, efficient, and responsive, quietly orchestrating the multitasking we take for granted.